to look at two different states. I'll look at the ground state. The ground state has an energy of 1/2 h bar omega, right? And what I'm going to set that equal to now is 1/2 k amplitude squared. Now, am I going to have the same amplitude for every one of these vibrational states? No, because as we go to higher energy, what's going to happen to the wave function? It's going to spread out. So I'm going to write this as the amplitude of vibration for the ground state. And I guess we have the k value calculated here. I'm actually going to do this though. Let's get the 1/2 gone. And let's make a substitution on this side. I'm going to take the omega out and put in k over mu to the 1/2 and set that equal to k amplitude squared. And then what we can do also is, I guess we can square both sides. And we can cancel out one of these k's. We're going to end up with amplitude to the 4th power is equal to, what do we got? The k's are gone. This is gone. We're going to get h bar squared over mu times k. I guess we're going to take a 4th power now. So, yeah. All right. So if we know the bond stiffness and the reduced mass and Planck's constant, I guess we could have done it from here. We go through and calculate what the amplitude of vibration is. I got this. I got 4.8 picometers. Just kind of a reality check here. Does that seem reasonable?
You put to the 1/2.
1/4. Thank you. So doing this calculation leads to this 4.8 picometers. Does that seem too big, too small, or about right? Seems about right because why?
The size of the molecule is like 1/3 or something.
Exactly.
1/13.
So what we found was the size of the molecule was like 113 picometers. Right? On average, 113 picometers between the two nuclei. How much vibration are we getting? 4 or 5 picometers. Okay, so that varies 4 or 5 picometers. If I try this for the first state, first excited state, this is going to become 3/2 h bar omega, and I can set that to 1/2 k times the amplitude for the first state. And check this out too. Go through, see if you can find your way through the formulas. For the amplitude of vibration in the first excited state, that went up to 8.3 picometers. Okay, so good sized jump between those two states. And then you can look at the amplitudes of the second and third and fourth, and at some point, something's got to give, right? At some point, we will get amplitudes larger than the bond lengths, and at that point, we've got to ask what actually happens. And typically, the molecule comes apart. All right, any questions on any of that? Vibration, rotation, quantum state? Okay. So now we're going to move into kind of the second half of the chapter. First half of the chapter was molecules, right? So we looked at diatomic molecules, rotational and vibrational energy states. Now what we want to do is take a look at some examples of solids. And the example we're going to look at is metallic solids. So I brought in a sample here. So let's talk about a little bit about metals. And we said that metals have this nice feature to them that, what's the chemical formula for this? And you go, well, any number of atoms can join, right? In fact, I can make alloys. I could mix different elements together, and I can still get it to form a metallic solid. What's going on with that? So let's pick a metal. I'm going to pick copper. And I'm picking copper because this is made out of brass. Okay, and brass is mostly copper. And I wanted to pick an easy example to work from. So if I have a single copper atom, what would the electron configuration be? One copper atom. Okay, so we're supposed to be able to just read down the periodic table, right? The first row does what? 1s2. The next row does what? 2s2, 2p6. Next row, 3s2, 3p6. Am I down to copper yet? Well, we're down to the row. So we're down to the row where copper is going to show up. So what I can do, copper showed up in this row. So I can write these down very rapidly. And I'm going to take all of these, and I'm going to say, those are definitely core. There's just no question. These are definitely core electrons. And core electrons are going to tend to stay with a particular nucleus. So these guys are going to pretty much, here's a copper atom comes in, the core electrons stay with that nucleus. But anything on the next row, the one where copper actually appears in the periodic table, potentially these could be part of the chemical bonding that's going on in that block of metal. So let's see, what does it look like on that next row? Yeah, I got to come over how far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I need 11 more electrons. So copper is element number 29. And how many definitely core electrons did we just identify? 2, 2 plus 6, 2 plus 6, 2, 8, 8. Sounds like 18. So I'm going to have to place 11 electrons in here somewhere. And where are they going to go? Yeah, they're going to go into some combination of 4s and 3d, right? Well, the details of this are, we get to look at the back of our book and say, experiments say 3d10, 4s1. So I'm going to write it like that. 3d10, 4s1. Are these likely to be involved in chemical bonding? And by chemical bonding, I mean metal bonding, holding the piece of metal together.
The S1?
Yeah.
The 3d10.
Yeah.
And why not?
It's not the outer.
Yeah, because it's a filled suborbital, right? So
Yeah.
this is that chemistry
It's not the
stuff.
outer.
So we're guessing that predominantly the copper is going to be held together with the 4s1 electrons. So here's how that works. Each copper atom that comes in and wants to join on to the existing copper atoms, what do they have to put in? And you go, well, every copper atom that comes in. Here is the buy-in fee for the copper atoms. Each copper atom has to bring in 2 4s states and 1 4s electron. And what all copper atoms are going to do is they say, sure, you can keep all of your core electrons, that's fine, don't worry about it. We want everybody to donate 2 4s states. We're going to take those and we're going to mix them all together and form quantum states that hold everybody together. So this is like taking different linear combinations of functions. So we're going to take the linear combination of everyone's quantum states, and we're going to come up with a set of quantum states that are delocalized. And delocalization means what? Yeah, instead of the electron stuck in one region, they can spread out. Maybe the electron wanders around most of this block. Once we form this, there could be wave functions where there's a probability of an electron being kind of anywhere inside this block. We have to allow for the possibility that it's just really probability is spread out. And that's holding everything together. Okay, so what you've got are a bunch of copper nuclei surrounded by their core electrons. Do the core electrons cancel out all of the charges on the nucleus? not all of them, right? There's a leftover positive charge still. And that holds these 4s electrons in place, but the 4s electrons themselves, we're going to say, are spread out. That's what's holding everything together. A sea of electrons is the way this often gets presented. Now, how complicated is it going to be if we go in and try and keep track of every copper nucleus inside here and develop wave functions where the electrons are interacting with all of the nuclei? That sounds too complicated. So we're going to do an approximation. We're going to say that all the nuclei with their core electrons constitute a kind of roughly uniform positive charge throughout the block of copper. So here's our block of copper. The positive charges are coming from nuclei plus core electrons. And then what we're going to do is we're going to add the 4s electrons in, and they're going to fill in all of these regions. We're going to have a bunch of 4s electrons holding everything together. So that's the plan. Now we're going to say that is approximately the same thing as a three-dimensional infinite potential well. Why do we get to say that?
The electrons can't be stuck.
Because it is, right? Yeah, the electrons are stuck inside. So if I have an electron, with a probability distribution, what has to happen to the probability distributions at the edges? They got to drop down to 0, right? Because at the edges, it's not going to be moving around kind of uniformly in this positive region. Electrons, once they get to the edges, are going to be seeing positive charges in just one direction. And that creates a wall, effectively, that says that if I shake this, are electrons going to fly off? You go, no, because they're in an infinite potential well. So what we can do is go back and, anybody remember the infinite potential well? Let's see, in one dimension, our infinite potential well looked like a normalization constant times sine of n pi x over L. That was in one dimension. Okay. How do we extend that to 3? You'll notice the reason I actually brought this in, I brought this in, because it's a cube. Right? And I don't want to do this in spherical coordinates. So that's
we'd never write that again, right?
What's that?
You said we'd never write that formula again.
That's right. So we don't want to do this in spherical coordinates. Here's the argument. The argument is, we're going to imagine what's going on in a cube, and then we're going to say, if the metal were in a different shape, it's not going to be very different, right? So we kind of ignore edge effects. We go, whatever features come out of here are going to apply for all different shaped objects. So here we go. Now, what were the boundary conditions here? Put on your three-dimensional viewing caps, right? Boundary conditions. Sorry about that. I apologize. Boundary conditions here were what? Wave function equals 0 where? X equals 0, X equals L. Right? Oh, I forgot to say that. This is L by L by L. So X equals 0, X equals L. The wave function's got to go to 0. In 3 dimensions, I have 4 more boundary conditions. What are they? At y equals 0, y equals L, and z equals 0, z equals L. And I can meet that by taking a function that is a sine n pi x over L times the sine of n pi y over L times the sine of n pi z over L. I can just take products of the three wave functions, and that'll work. Okay, that will work as a wave function. Except I have to do something with my n's. I got three different n's going on. So I'm going to have to say, well, this is the n for the x direction, this is n for the y direction, and that's n for the z direction. Okay. And then, just to see how this would work, let's throw it back in the Schrodinger equation. I'm going to go through this fairly quick. If people want to see more details on it, they can. What would a three-dimensional Schrodinger equation look like for this? We would say that would be h bar over 2m, second partial with respect to x, plus second partial with respect to y, plus second partial with respect to z, times the wave function. And we're going to leave the potential energy off. We're going to treat that like a constant. And so all we're really looking at is kinetic energies, right? What do I get for the energy? What do I get when I take second derivatives of this wave function? If I take a partial with respect to x, how is that going to affect the y and z parts of the function? It won't, right? So that says when I'm taking my two derivatives with respect to x, I'm going to get the entire wave function back again with what factors out front? Yeah, I'm going to get a minus sign because a square sine function, two derivatives will give me a minus sign. And then I'll get nx squared pi squared over L squared times the wave function back again. What happens if I do this in the y and I do it in the z? The same thing will happen, right? So what will happen here is I'll end up with h bar squared over 2m pi squared over L squared times nx squared plus ny squared plus nz squared times the wave function back again. And that's my energy. So now I've got an energy for these electrons inside this three-dimensional container that looks like h squared over 8mL squared How is that different from my one-dimensional example? Back when we did one dimension, what did it look like? Exactly, yeah, exactly the same, except I didn't have those two extra quantum numbers. But everything else is exactly the same as before. Now this actually does complicate things because, let's go back and look at this. If I had a wave function in here where nx was equal to 1, ny was equal to 1, and nz was equal to 1, that would be my lowest energy quantum state. What would it look like? Where would the probability be for that electron? These are 3 sine squared functions multiplied by each other. What's that going to do? It's going to place most of the probability in the middle region, right? And it's going to drop off towards the edges. What if we did this? What if we looked at a quantum state that was nx is equal to 2, and y is equal to 2, and z is equal to 2? let's just look in the x direction. What would the wave function look like for nx equals 2? And that would say I would have a node, right? I would have a node here. I would have probability on this side, probability on this side, but I'd have a node down the middle. And if I'm in quantum state 2, 2, 2, I would have more nodes, right? I would have one here, and I would have one here. And that would divide that into 8 regions. And I would have probabilities kind of in the center of each of the 8 regions. And then I would have a set of nodal planes where the probabilities are 0. And that's what happens in, so it's the same thing that happened in 1 dimension, but now I got to keep track of how many nodes do I have in each of 3 dimensions instead. All right, so anyway, that's the idea with these wave functions. That's what they're going to look like. And this is what their energies are going to be.
Is that h bar squared?
It's not, so I
Okay.
cheated there too. What I did was, this was h bar, and that was pi. So I got rid of my h bar and my pi, and replaced it with a couple of factors of 2. So you're right, I switched from h bar back into h. That's because that's how we had derived it back when we did 1 dimension. All right, now the question is, how do I count all of the possible quantum states in 3 dimensions? Because it becomes a real problem in counting nx, ny, nz. What are the possibilities for these 3 quantum numbers? Well, it could be 1, 1, 1. 1, 1, 1 would be the ground state, right? What would be the next excited state above the ground state? Well, I could have this as 2, 1, 1, or I could have this as 1, 2, 1, have this as 1, 1, 2. That's 3 separate quantum states, but they would all have the same energy. 3 different looking wave functions. Well, they actually look similar. How would the state 2, 1, 1 be different from 1, 2, 1 be different from 1, 1, 2? Yeah, each one would have one nodal plane, but this would be a nodal plane along the x-axis, this would be along the y, and this would be along the z. So they look like t-orbitals, right? I get something with a lobe here and a lobe here, and then I get something a lobe here and a lobe here, and I would get something with a lobe here and a lobe here. Okay, so we're seeing kind of the same features with these nodes, and then you can just go up and count what other states are present. That's not a trivial counting problem, so we got to think of some clever way of just keeping track of how many states do we actually have. Anybody have this time? What time do we have? 2, 8. Okay. And here's how we count how many states are present. I'm going to do a quantum state space. We'll draw a couple of axes here. Quantum state space. Right, so one axis is keeping track of the quantum numbers in the x, one in the y, one in the z. Each set of integer values is going to correspond to a unit cube. Each cube has a volume of 1. Okay, so for example, if I have the 1, 1, 1 state, the coordinate 1, 1, 1 is right there, and that cube represents a certain amount of volume, and that's that state. If I looked at the 1, 1, 2, or the 1, 2, 1, or the 2, where would those be? And 1 would be here, and 1 would be here, and the other one would be there. So every time I come up with a new set of quantum numbers, following the rules over here, I'm going to get one more cube in this space. Okay. Now, how many atoms are in this block of copper? It's lots. Do we want to write down all of the quantum states? No. Okay. What we do want to do, though, is we want to come up with a way of counting how many states are in there. And what we do is we say, look, by the time we get up to these huge values of nx and ny and nz, it's going to look like a sphere, right? What we can do is take this energy formula that we've got right here and say the energy could be written as n squared h squared over 8m L squared, where n squared is nx squared plus ny squared plus nz squared. So that says that the way these quantum states get filled is we start with the ground state. Ground state's right at the origin, right? Every time we move away from the origin, we're kind of at a new layer of energies. And we move out to the next layer, we move out to the next layer, we move out to the next layer. So once I filled in all these zillions of electrons, what we're going to have is a bunch of cubes that look sort of like an eighth of a sphere. And the number of states is going to be equal to 1/8 the volume of a sphere. So again, it's this sort of interesting, clever counting technique that is used to count how many quantum states we've got here. So the number of states that we have is going to, and I'm going to change this a little bit. I'm going to put in the 1/8. I'm going to put in a factor of 2 to account for spin up and spin down. So every one of the states that we come up with inside this cube is going to have the possibility of a spin up electron and a spin down. That puts in a factor of 2. And then what is the volume of a sphere in my quantum state space? Yeah, it'd be 4/3 pi n to the third. So we're trying to get away from these little n's, which are hard to determine, and convert it into something where we're just counting the number of states. Something where we can just count 1, 2, 3, 4, 5. This is how many states we've got at this point. And it says that the number of states that we'll have once we reach a certain energy is going to be given by pi/3 n to the third. Okay, let's get our energy formula back over here. So here is our energy formula, and it says, I'm going to write this as h squared 8m. And then in the numerator I have n squared, in the denominator I have L squared. And I'm going to take the n on top and convert it into number of states. So I'm going to take this n and write it as 3/pi n states. Now at the same time, I'm going to take L squared and get rid of L squared and rewrite it as a volume. Yeah, question? Oh yes, thank you. Thank you. All right, I want to do the same thing with L squared. What I want to say is that the volume of this cube is L to the third. That says that L is equal to V to the 1/3. So when I make those two changes, I'm going to get h squared over 8m, 3/pi, number of states, divided by V, all to the third power. And now I've got a formula for the energy of the nth state, where n just goes 1, 2, 3, 4, 5. I don't have to do any difficult comparisons between different quantum numbers. I just have one quantum number that tells me how much energy I will have at each one of the possible states. All right. Any questions on that? So if this is a piece of copper, how many atoms would I have in a particular volume? Because this is what the energy is saying it depends on. The formula that we came up with says that the pattern of energy states inside a piece of metal with electrons all over the place, the pattern of energy states for those electrons is going to depend on Well, h squared over 8m, that's not going to change, right? Planck's constant's not changing. This is the mass of what? Mass of an electron. So this part's not changing. 3 over pi is not going to change. I just have to know how many atoms there are. So let's ask this problem, and then I think we'll have to wrap it up here and move over to the other room. For copper, how can I calculate the number of atoms per volume? How many atoms of copper are there in a certain volume? What would I need to know? 2 things. Molar mass, density. That's it. So I need a molar mass and a density. And the molar mass will, I can start with, I want number of atoms. We'll say Avogadro's number of atoms for copper, how much mass would that be? 63.5 grams. And then what's the density of copper? And the density of copper is 8.96 grams per cubic centimeter. And then I actually did this. I converted the cubic centimeters into cubic picometers. Or cubic nanometers, sorry. I used because I didn't want big numbers. And I have to do that 3 times. So what I got for copper is the number of atoms per volume in a block of copper is 85 atoms per cubic nanometer. That's a good number to know, right? If I take a look at just 1 cubic nanometer of copper, there's going to be about 85 atoms in that region. Okay, and I can put that back into here, and that's going to allow us to say stuff about the energy states. So let me stop here, and then we'll pick up in the other room at 2:30. Questions? Any questions on this? Okay, how many of you guys take chemistry? Okay, so yeah, this is supposed to be going a little beyond. Well, it's beyond anything you see in chemistry, I think, is my guess.